All right, folks, we are almost done this unit. We are going to start this last section off with another example. This is determining molar mass from osmotic pressure. This is one of the main uses of osmotic pressure is that it can be easily measured and it allows us to determine molar masses of unknown substances. So this question asks, biochemists have discovered more than 400 mutant varieties of hemoglobin, the blood protein that carries oxygen. A physician dissolves 21.5 milligrams of one variety, presumably an unknown variety, in water to make 1.5 mils of solution at 5 degrees Celsius. She measures an osmotic pressure, 3.61 torr. What's the molar mass of the protein? So, equation we want to use is pi equals I C R T, where we're going to make the assumption here that the protein itself does not dissociate in water, which makes sense because it's an organic substance. It's not a salt, which is just CRT. We can drop the Van't Hoff factor. And we're going to rearrange this because what we want to find out is concentration. And concentration is going to be equal to pi over RT. So once we have the concentration, we can use the volume to get the number of moles, and because then we have milligrams and moles, we can figure out the molar mass, which helps to identify what the molecule might be. So we'll start out using this particular equation right here. The concentration of this solution that the physician is looking at is going to be equal to the osmotic pressure pi, which is 3.61 torr, divided by, first of all, R. And the value of R we want to use in this example is the value of R that has torr, which is equal to 62.36. And this is liters torr per mole K. And multiply by the temperature, which is in Kelvin. So we have 5 degrees Celsius. So that's equal to 278.2 Kelvin. And the units of Kelvin will cancel, the units of torr will cancel, and we get our final concentration here as 2.08 times 10 to the minus 4 moles per liter. So from this in the volume, we can get number of moles, where N is equal to concentration times volume, which is 2.08 times 10 to the minus 4 moles per liter times the volume, which is 1.50 mils, or 0.00150 liters. And that gives us a quite small number of 3.12 times 10 to the minus 7 moles. So now we can just get molar mass, where molar mass, use my fancy M, is the mass over the moles, which is 0.00215 grams. This is the number here in milligrams converted to grams, divided by 3.12 times 10 to the minus 7 moles. And that gives us a value of 6.89 times 10 to the plus 4 grams per mole. And that's quite heavy, but that's typical of proteins. Proteins are quite large molecules. So this makes some total sense for us, which is great. All right, the last thing we wanted to talk about is something called reverse osmosis, which I indicated before, where if you take this hypothetical situation where you have brine and water, osmosis is going to want the water to go from the pure side with low solute concentration over to the side of the brine with has a high solute concentration. But you can pressurize the side with the high concentration of dissolved solid that will force pure water to go through that membrane, and it allows us to take basically what's on the right hand side, which is dirty water, or water with maybe unwanted solids dissolved in it, and by applying pressure to it with a membrane, we can generate pure solute-free water on the right-hand side. So this is used for drinking water. It's used for making DI water in labs, deionized water, because ions typically can't pass through the membranes that are often used. You can do this on a large scale. And if an area lacks a source of fresh water, but is, say, close to the ocean, so has lots of salt water, you could use salt water and reverse osmosis to remove the salt from the water, a process called desalination. And that would provide a certain amount of drinking water. Or if you happen to be in an area where you are having well water that has undesirably high concentrations of various solutes, things like salts of iron or other metals, you can use reverse osmosis to convert that into much more palatable water. It's also used in the production of maple syrup, because for maple syrup, basically what you have coming out of the tree is a solution of sugar and water. To convert that into maple syrup, you have to remove around 90% of the water. And the traditional way is to boil it off, but boiling requires a crazy amount of energy. So with reverse osmosis, what they actually do is reduce the volume by taking the majority of the water out by compressing the sugar water, which forces pure water out through the membrane and keeps the sugar solution inside. So it's a much more energy efficient way of reducing the volume of the sap. And using this, you can, first of all, greatly save money, but then the resulting syrup that's produced after reverse osmosis, you can boil that down the rest of the way and give it the same flavor that it would have otherwise. All right, that's it. So we are finished this unit on phase equilibria and solutions, and that's it for this semester as well. So see you soon.